we are discussing the relations, and last day we have seen a special type of relation, mainly it comes under the properties of relation, is the equivalence relation. Now, we often use relations to order some or all of the elements of a set, and for this we use some properties of relations. The three basic properties that we have read, the reflexive, symmetric, we will see today some variant of symmetric, and the transitive property that are mainly used. But here the relation is called the something called partial ordering. So, today we will see how relations are used to order the elements of a set. So, we will read the partial ordering, or sometimes we call partial order. Okay. Now, when we use the relations to order the elements of a set, say if we see some example that we use relations to order the elements of a set. This is a general thing. Now, as an example, I can tell that to order the set of integers containing the pair of elements say x y, and the relation is less than or greater than, relation is less than, say x less than y. Normally we call x r y, where r is the relation is the less than. Or we use the to order the words. So, we write other example that to order words using the relation containing a pair of words say x y, again I think, when x comes before y. So, here if we consider our alphabet set, say A to Z, in order, that means as if A is in position 1, B 2, C 3, and this is Z in 26. So, this is in some order, and this ordering will govern that which letter comes before y. say x comes before y if x position is less than the position of y, and here positions means that 1, 2, 3. And normally this is the ordering we use in dictionary, and that will be again in details we will be describing later. Now, another example we can think, say on more practical example, that we can schedule the tasks of a project again using the relation say a relation of a pair x y, pair of tasks x y, a pair of tasks and the relation is such that x must be terminated before y begins. So, for this type of examples we can use relation, and this is some particular properties that mainly the reflexive, the antisymmetric and the transitive properties are used for that. So, we define the partial ordering first. So, a relation R on a set X is called a partial ordering if the relation is reflexive, transitive and antisymmetric. Now, if we remember that instead of antisymmetric, if it is symmetric, then last day we have defined that as a equivalence relation. Now, a set X along with this relation R is called the partially ordered set. Or more commonly the term is used called the poset. normally we denote that as the term, here it is x along with the relation R, we call this is my poset. Okay. And the elements of x, or members of x, are called the elements of poset. Now, we see first one simple example. We see some example. So, show that greater than operation, that the relation greater than equal to, okay, right, is a partial order or partial ordering on the set of integers. Now, let the relation is R, is greater than, and the set of integers, normally we denote as Z. Now, see what are the properties the relation holds. Previous example 1 continued. Now, if I consider a pair, say AB. So, if or AB belongs to Z. So, I am considering the set Z and the relation is greater than equal to, and I am checking whether it is a poset or not. Okay. Now, AB belongs to Z. So, my relation is R is greater than equal to. So, if I write A R A, since A equal to A, so A R A holds, A R A is true, that means my relation R is, so A R A is true. So, the relation is reflexive. Now, if I consider that some relation A R B, that means A greater than equal to B. I consider B R C, that means B greater than equal to C, where A B C all belongs to Z. Then since it is positive integer or a set of integers. So, I can write that A. So, A greater than equal to C, that means A or C holds, that is A or C holds. So, it is transitive. Now, if A or B if I consider A or B and A not equal to B, since my relation is greater than equal to, so that means here I have to consider only greater than, that means A or B and A not equal to B means only A greater than B. So, now if I consider A greater than B, that means if we remember the definition of antisymmetric, that means A or B, and if A not equal to B, then B for this relation greater than B or A, this is it holds, because never B or A is true. This is true, that means if A greater than B, then B cannot be greater than, since A greater than B. So, B cannot be greater than A. So, this relation is antisymmetric. So, my Z greater than equal to, this is this set of integers with the relation greater than equal to is a poset, is a partially ordered set. Now, we see another example. We give example 2 as the, instead of the greater than equal to, we take one relation, the divisibility. So, we show that the divisibility relation is a partial ordering on set of positive integers normally we denote as Z plus, and the relation we denote, relation R we denote as the by division. So, we have to show whether we have to show that the Z plus with the relation divisibility is a, so this is a poset. Now, first we see the reflexive. See, always A or A is true, since A divides A. A is positive integer, that A belongs to Z plus. So, it is reflexive. So, it is reflexive. It is also transitive, because if A are B and B are C, that means that is A divides B, B divides C. So, I can conclude that so A divides C. So, it is transitive. It is transitive. Now, what about the antisymmetric? Say if A or B holds, that means A divides B, that is A divides B. So, if A not equal to B, if A not equal to B, then B or A is never true. That means B is not in this relation A. So, this is antisymmetric. So, this is antisymmetric. So, Z plus is a, so this is a proved, this is a poset. Yes, it is a poset. Now, we show a different type of example. In the last lecture, we have defined the power set, which is nothing but the all the subsets of a set. Now, we show that the relation inclusion, set inclusion. So, show that the relation that means if it is a subset, that is a inclusion is a partial order or partial ordering on the power set P S, where S is the or power set P S of set S. So, power set, if I remember that power set is the set of all subsets of S, of set S. Now, we consider a subset A. Okay. So, if A is a subset of A, or we know that it is always true that A is a subset of A. So, A or A holds, which tells that it is reflexive. Now, if A is a subset of B and B is also a subset of A. That means A are A are B and B are A. If both hold, then we know that A equal to B. So, if A not equal to B, then it does not hold. So, that means it is antisymmetric, because if it is A equal to B, then actually the condition is false for antisymmetric property, and so it is vacuously true. That means, for condition to be the relation one to be antisymmetric is A not equal to B. So, then it is antisymmetric. So, A are B and B are A hold, then A equal to B. So, it is then it is vacuously true. So, the property of or that the relation to be antisymmetric, or the I can write the condition that the relation to be antisymmetric is false. So, antisymmetric property. So, it is vacuously true. Now, we have if A is a subset of B and B is a subset of C. So, from the definition of subset, we know that A is a subset of C. So, which directly gives that it is transitive. So, we can tell that my relation with the partial order set. So, the conclusion is the partial order set on P S with the subset, this is a poset, this is a partial ordering. Now, we see one example when the relation is not a poset. Let R be a relation on the set of people such that the relation holds that A or B if A, B are two people and A is older than B. This is the relation. A is older than B. So, this is my relation. So, we have to show show that R is not a poset, R is not a partial ordering. Now, we see that the relation is older than. So, first we see that we take 3 people A, B, C such that A or B, that means A is older than B, B or C, that means B is older than C, and which means that so A is A or C holds that is A is older than C. So, it is transitive. So, it is transitive. What about antisymmetric? Because A is older than B, so B cannot be older than A. If A or B, that is A is older than B, then B or A never holds. So, that means this is antisymmetric. So, this is antisymmetric. But see that A is older than B. So, A or A, that one person can never be older than himself or herself. So, A or A, it never holds. A or A never holds, since one person cannot be older than himself or herself. So, it is not reflexive. So, the relation is not reflexive, not reflexive. So, it is not a, the conclusion is that relation is, it is not a, R is not a partial ordering. Now, we can define that in this relation, one thing is called the total order, because we read the term partial order. So, what is total order? For that we define a comparable or incomparable set. The element A and B of a poset, if it is a partial order set, say in X R, is comparable if A R B or B R A holds. That means, if I consider the relation R as the say less than equal to, then either A less than equal to B or B less than equal to A holds, then it is a comparable, then this comparable. But say if I consider say relation is a divisibility property, then A divides B or B divides A, that is comparable, but not for all sets it may not be true. Then it is called, then if it is not, if that means if neither A are B or B are A hold, then it is incomparable. Now if I know the comparable and incomparable, so I can define the total order say total order of set X, and I take a relation like this is a, or I can give the simply I can give the relation R is a poset and every pair or every pair of elements are comparable. Then X is called a totally ordered. So, just now we have seen that the set of integers z and less than equal to this is a totally ordered set, because if I consider any two elements in the set, they are actually comparable. But if I consider positive integer z plus and division, then not a totally ordered set. Since if I consider say 3 and 7 this pair, then 3 or 7 or 7 or 3, that means 3 does not divide 7, 3 does not divide 7 or 7 does not divide 3. So, 7 or 3 they do not hold. So, it is not a totally ordered set. So, well ordered we can define as the, so well ordered earlier we have defined, now we give a different definition, that if it is the set X with a relation R is a poset where the relation R is a totally order, where R is a totally order or total ordering. Better I write R is a total ordering. And every non-empty set subset of X has a least element. Okay. Now, the most important application in POSET is the lexicographic ordering in dictionary. We know this is lexicographic ordering. All of we know that in dictionary that normally the words appear according to the ordering of their letters, and we can show that how these POSET or how these constructions work in a POSET. So, how these constructions work in a POSET. So, if we define, say I have a POSET A1, say less than equal to, I have another POSET A2, then I can take some Cartesian product of these POSETs, because finally these are all sets with some relation. So, we can take Cartesian product of say A1 cross A2 cross, say if I have some AN. Now, how I define this Cartesian product? Say if, so I consider some two pairs, A1 A2 and B1 B2. Now, either A1 less than A2 or A1 equal to A2 and for some integer I that I can consider that, or some I greater than 0, that A1 equal to A1 equal to this is A1 equal to A2, this is wrong, A1 equal to B1. This is okay. Since we are considering A1 A2 and B1 B2, so this is A1 less than B1, or if A1 equal to B1 and for some integer I greater than A1 equal to B1, A2 equal to B2, like AI equal to BI, then the next AI plus 1 less than BI plus 1. Then the lexicographic ordering is that the words say A1, A2, that AI, AI plus 1, that is ordering is like that B1, B2, B3, BI, BI plus 1. Normally, this is mainly used in our arrangement of dictionary. So, lexicographic ordering, which is nothing but the application of poset that is mainly used in our dictionary. So, how these relation and their property are used for practical purposes, this is one of the examples.